Hi team, welcome to this, which is the fourth video for forces of motion, and this is looking at motion in 2 dimensions, which will start using vectors when we're doing our calculations of acceleration force. Now, again, we're going to be using Newton's second law, which is that the resultant force applied to an object is proportional to the acceleration of that object. And we know by now that the constant of proportionality we're going to be using is the mass. We do need to know, though, that there's 2 key ways we can apply this particular rule, and we need to keep them separate. We can flip between these 2 ways, but we need to keep them distinct. The first is that we can use scalars or magnitudes of our force or acceleration. So the force is proportional to acceleration, and F equals ma. And in this case, we're putting in the magnitude of the force if we want to calculate the magnitude of the acceleration. The second way will be using vectors, where we might say that F equals ma, where we have bolded, or I've bolded F and A, and we might write it in our books as F equals ma to represent that we're using vectors. And we're always going to be underlining those vectors. And in this case, we're going to be adding in the vectors and multiplying by the scalar of mass. Now, it is very, very important that we notice that if I put in a scalar version of the force, I will get out a scalar version of the acceleration. An equation should not be that I have a scalar version of force will equal mass times a vector version of acceleration. That will not work, and we will not get the answer we want from it. Okay, so we need to make sure that we cannot mix and match. We need to remember that we cannot mix and match. So if we are asked to find a magnitude of the acceleration, then we need to substitute in a magnitude of the force, or we need to find the vector form of the acceleration and then find the magnitude. We'll use both techniques. The other thing to notice is that the acceleration will always be a scalar. My mass does not have a direction. Okay, the weight that mass causes does, but the mass itself has no direction. Okay, so mass will always be a scalar. So let's look at 2 quick examples, and then you'll be ready to get started. The first is this one. Please have a quick read of it. Now, this question will rely on 1 key bit of knowledge from the second sheet, which is that if we want to find the acceleration A, we're going to use F equals ma, but we need to remember that our resultant force F is the sum of the forces acting on a body. Okay, so it's going to be the sum of F1 and F2. And now I will work in column vectors, so I'm going to have 5, 6, plus -2, 9, which will give me a resultant force of 3, 15. Now I'm asked to calculate the acceleration A. Now you see here that A is bolded, so that means that this is a vector quantity. And the question might not always be incredibly specific, but we'll be able to see from the question what it's asking us. So I want to find the vector quantity, so I know that my resultant force, 3, 15, will equal the mass, which is 2.5, multiplied by an acceleration A. Now, we then need 2 variables for the kind of I component of A and the J component of A. I'm just going to use X and Y, okay, but it doesn't really matter what we use. This will give us 2 equations. This will tell me that 3 needs to equal 2.5 times X, and that 15 needs to equal 2.5 times Y. Okay? This top equation gives me a value of X, which is 3 over 2.5, which is 1.2. And this second equation gives me Y is 15 divided by 2.5, which is 6. Okay? Now, that means that my acceleration vector is equal to 1.26. And that is my final answer for part A. Okay. Now for part B, I want to calculate the displacement of the particle after 3 seconds. And again, when we talk about displacement, this should hint straight towards us using suvat. So displacement is the thing I want. I'm told the particle is at rest to begin with, so my initial velocity is 0 meters per second. Now it wants me to find. Now I also have a time of 3 seconds. Okay. Now we also have this acceleration, which is a vector. Now sometimes we might be tempted for me to write 1.2i plus 6j. But I'm not going to be able to substitute in a vector quantity when I've got kind of magnitudes. So I need to get rid of this, and I need to find my magnitude of the acceleration to sub into SUVAT. Okay, the magnitude of my acceleration is going to be 1.2 squared plus 6 squared and square rooted. Okay, now that is 6.12 meters per second squared, and that is to 2 decimal places. Okay, 6.12 meters per second squared, and so I can add that in to my variables. Now, because I want this displacement and I have so I've got u, a, and t, all I need to use is s equals ut plus half at squared. Now, ut will go to 0, 0 times t is just going to be 0, plus 1 half times by 6.12 times by 3 squared. And my answer here is going to be that the displacement will be 27.54 meters. Okay, 27.54 meters. And so key thing here is if we're substituting in to SUVAT, I will need the magnitude. So I will sometimes have to move from a vector quantity into a magnitude before I then substitute into my equations, my SUVAT equations. Let's look at one more example. So we're told that a particle accelerates at 10 meters per second squared and is acted on by the resultant force R equals negative 5I minus 7J newtons. I want to calculate the mass of the particle. Okay, so I know that my resultant force R will equal the mass times the acceleration. Okay, but I need to notice here that I've been given a magnitude. So I can't say that minus 5 minus 7 equals mass times 10, because this equation is mixing a vector with a scalar, and so my value of mass will be a vector, which I do not want. So I actually need to say and start using, okay, that the resultant force, the magnitude of the resultant force is equal to the mass times the acceleration. That means I need to calculate for myself the magnitude of the resultant force, which is as easy as just doing negative 5 squared plus negative 7 squared, and then square root my answer. So I'm going to do the square root of 25 plus 49, which is 8.60 newtons. And so I know that 8.60 newtons equals the mass times the acceleration of 10, which means my mass is equal to 0.86 kilograms. Okay, that's just doing 8.6 divided by 10. So 0.86 kilograms. Easy as that. Key thing with this is knowing that we cannot mix and match our vectors and our magnitudes. Any issues with the sheet, let me know. Otherwise, good luck.